Okay, we're working with our similarity notes for day 6. Been working on dilations for a while, and we're going to make that connection piece between similarity and dilations. So if you remember, we're going to start with some of that vocabulary. Dilation, where all side lengths are going to be multiplied by the scale factor. And the angles are preserved. What does that mean? The image is going to get bigger or smaller, but the shape does not change, nor will the angle measurements. Okay. So in sense, we say that the two images have the same shape, but they are going to be different sizes. Okay. All right, so way back at the beginning of Unit 5, we covered the idea of what corresponding is. So I'll refresh you. It's going to be angles or sides that are in the same spot, but on the other shape. Okay, and we'll talk about a little bit more what that means as we move forward. All right, now similar is one of our newer words. Okay, similar is if the two shapes are said to be similar if all pairs of, we're going to talk about corresponding sides. Okay, remember that's going to be kind of like matching sides. Are proportional. So remember, when we're talking about a proportion, we're just talking about two fractions that we set up where we'll cross multiply to solve for a missing piece. So that's what that means by proportional. And the corresponding angles are equal. Okay, so our symbol for similar is it looks like a congruency symbol, but just the top part of it. So that little squiggle that we see is what similarity means. Okay. So we talked about proportional up here, where we talked about actually being able to set up two fractions. Okay. We've also been dealing somewhat with a little bit of proportional when we were talking about a scale factor. Okay. Well, K can't change, and that's what we mean by constant. Means that we're going to multiply all the sides by the K. Okay, we also call this a scale factor. It's what makes our image bigger or smaller. Okay, so we're going to take all of these words and tie them into our lesson today. In the diagram below, we know that triangle ABC is similar to triangle DEF. Okay. So if you remember anything, the first one will always be your pre-image. So this is pre, this is what I'm going to start with. And then DEF is then going to be my image. It's the one that has been dilated. So up above we mentioned the word. Okay, use tracing paper to verify that all corresponding angles or angle pairs between the two triangles are the same measure. Right. So we first want to be able to pair up what matches with angle A. So if we look up above, A is in the first position, so is D on the second triangle. So that means angle A matches with angle D. And angle B is in the second position, so it's going to match with the letter here in the second position, which is angle E. And C is going to match with angle F because that is in the third position. Okay. Now I can take tracing paper and verify that the angles match. Okay. So if I trace angle A, I can shift it down and you can see, yep, it matched angle D. And essentially I could do that to all the angles, but I shall not do that at this time. So those are the angles that match. All right. Now we're going to pull it in the idea that they're going to be similar if we have this idea of a scale factor. Okay. So from the pre-image to the big image, we need to figure out what we're multiplying by. That's the idea here that they tell us scale factor. What are you multiplying by? Okay. So if I look at the two triangles, I need to find corresponding sides that have numbers. So if I take a look in the diagram, I see that AC has a number, and A to C goes from 1 to 3. So its matching side would be D to F, which is also the first to the third. And yep, they do indeed have numbers. So to figure out the scale factor, I have to figure out what am I multiplying the pre-image by to get to the image. Okay, well, 7 times the scale factor, which we call K, is going to have to equal 14. Now most students right away will pick up that K is 2. So therefore, the scale factor is 2. Now remember, we talked about this being a constant, which means it's going to happen to every single side. Okay. So now if I'm looking, the other side they gave me on the pre-image was CB. So I'm going to look, C to B is 3 to 2. It's going to match 3 to 2, which is F to E. And that just happens to be one of the problems that we're trying to figure out down below. We're trying to figure out how much does FE equal? Well, FE is going to equal its corresponding side times 2, because this is the original. So we're taking the original and multiplying it by 2. So FE equals 2 of CB. Well, we know what CB is. They told us CB is 8. So that's going to give us 2 times 8, which is 16. And then we have one more side that I need to pair. Well, I already used 2 of them. So the third sides have to be proportional to each other. They have to match. Okay. So AB is then the original. Well, that means 2 times AB is going to give me the image of 20. So then we have to think to ourselves, 2 times what is going to give me 20? Well, most of you guys can figure that out. We just divide by 2 on both sides and get the idea that AB equals 10. Okay, so that's how a scale factor works, and that's how we're pairing up corresponding angles and corresponding sides. So now if I was to write all of these as as proportions, I would put AC over DF. Small over the big. It's going to equal the small, the green side, CB, over the big green side, FE. And AB, small, is going to match the big of DE. So this is how we would write all of them as proportional side measures corresponding as we did with the angles up here. All right, moving on with the lesson. Now we're going to start to talk about similarity transformations. Well, when we talked about the word similar on the previous page, we were talking about a dilation. So a similarity transformation will occur when a dilation, okay? 2 geometrics are similar if there exists a similarity transformation that will map one figure onto the other. Okay. This transformation is either only a dilation, meaning we're making the image bigger or smaller, or it's a dilation combined with a rigid motion. Okay, we've talked about rigid motions in Unit 2 and the later part of Unit 5. Okay, a rigid motion is a transformation that preserves, now remember preserves means to keep, size, shape, and angles. And they're all going to stay the same from one image to the next. Now remember, the rigid motions are translations, rotations, and reflections. So that's what we're going to keep in mind for the next exercise. Exercise 2. Given that triangle ABC and DEF are similar, remember they're not exactly the same, okay, with congruent angles marked. What does that mean? A has one mark in it, D has one mark in it, B has 2, E has 2, C has 3, and F has 3. What does that mean? Those are the corresponding angles. A matches with D, B matches with E, C matches with F. Okay, and they want us to give a similarity transformation. Now remember, a similarity transformation can either be a dilation alone or a dilation combined with a rigid motion. A key word for both? Dilation. So obviously, a dilation has occurred. So that's going to go in the first spot, a dilation. Now the next thing is even though that this got bigger to create triangle DEF, how do I get it from here to over to here is the question. Okay, so let's test a couple theories out. Now if I just shift this up or down and move it over, there's no way. So when I trace this, not only am I going to trace the image, I'm going to trace the angle marks and the letters. Now if I just try to slide this, which this is a translation, that's not going to match up. Angle A does not match with angle E. So translation is out. Okay, now some of you might be thinking, oh, that's a reflection. So let's try to reflect this triangle over. So remember, reflection means to flip. So I'm going to flip this over. Okay. Oh, that one matches. But the question is, does this one match? Well, this has one angle mark and this has 3. That does not match. Nor does the angle down here match. 1 does not match with an angle that has 3 in it. So that's out of the question. It's not a reflection. So I tried a translation. I tried a reflection. So the only other thing this could be is a rotation. So I'm going to use a capital R to denote rotation. Now the question is of how much or how many degrees. Okay, I'm doing a reference point here to symbolize, remember these are 90 degrees. So when I turn it once, that's a 190 degree. Okay. So I'm going to rotate this 90 degrees, and I'm going to fit it into this image. Well, 2 matches with 2, 1 matches with 1, and 3 matches with 3. So yep, it's a rotation. Okay. Now, that was only a rotation of 90 degrees. Okay. Because if you noticed, here, when I turned it, I only turned it once to get this back to looking like a plus sign. Okay, so therefore that was a rotation of 90. Okay. Moving on to number 3. exercise number 3. In the following diagram, it is known that BCN, collinear, that's what this means, and ACM are all on one line, so talking about that they're collinear, will give me the triangle ABC is similar to triangle MNC, meaning this is the original, this is the similarity. Okay, give a similarity transformation. Okay, now remember, similarity transformation always has to include a dilation. So we know the first one right away, a dilation. It's clear, this image got smaller or became smaller. Okay, so we know it shrunk. Now the question is, what else did it need to do to get angle A to map down to angle M? So we do need another rigid transformation. So again, the rigid transformations are translations, a shift left, down, up, or right, a rotation, which means to turn, or a reflection, meaning to flip. Okay. So let's take a look. Remember, when you do these, they have to match. Okay. So what I'm going to do is I'm going to trace the original, which is ABC. One angle and 2 angle marks. Okay. Now if I reflect this, it's going to flip. So I'm going to flip the paper like this. Does 1 arc mark match with 2 arc marks? Nope. And neither does 2 match with 1. So that's not it. The flip did not work. Okay, so rotation is out. Can I slide this? Nope. Slide doesn't work either. It's not going to get the angles to match up. So the only other thing I can do is to rotate it. Now remember, we are going to shrink the image first before I rotate it. So if you're watching, I'm turning this image till it kind of matches, looking like this one. Well, if you notice right away, C lines up. That matches. This matches. And if you notice, even though that this image is bigger than the below image, the angle still matches. And that's supposed to happen. 1 arc matches with 1 arc. And 2 arcs matches with 2 arcs. So the rotation is it. Now if you're paying attention, this is a rotation of 180 degrees. So I'm going to do this plus sign here. So to get it back to the original plus sign, that's a rotation of 90. And then getting it back to the plus sign again, that means I rotated it twice. So that was 180. So a dilation, then a rotation of 180 degrees, which means I turn the image upside down. Okay. All right, on to exercise number 4. ABC triangle is similar to triangle DEF. Now remember, similar means they're the same shape, but they're not the same size. It asks us in the first one, A, for the scaling factor. Needed to dilate this image so that it's going to be congruent to this image. I'm going to use AB. Now remember, A to B is the first and then the second. So I need to use the side that matches first to the second, which is side DE. And you can see it in the image. But they don't always give you a picture, so I was just making it a little bit more clear. Okay. I use this side because I can clearly just count the boxes. I don't have to use the distance formula and all that. A to B has a length of 4. ED has a length of 6. Okay, so remember, ABC is the original, and EDF is the one that we dilated. Okay, so we're going to dilate ABC to get to the dilated image, EDF. All right, so that means 4 times K, remember K stands for scaling factor, needs to give me 6. So I set it up. Divide by 4, divide by 4. Okay, now when you do this, 6 divided by 4 comes up on your calculator as 1.5, and you can convert that to a fraction of 3/2. Right, on to B. They ask you very specifically for a similarity transformation. Okay, a similarity transformation, again, is a dilation. Definitely know that one. We know how much we dilated it by this time. Oh, I wrote 3 over 3. I do apologize. 3 over 2. We know it's a dilation, so I'm going to do a capital D of 3/2. Okay, so when you see it like that, you understand that you're multiplying everything by 3/2. So that's the first one. Now when I dilate it, it's going to make it grow to here, where C is going to be untouched. That's the center of dilation. Okay, now how do we get this image over to here? Okay, most of you guys can see that, yes, it is a flip. I'm going to flip this image to land on top of here. Okay, A, if I flip it over, will match up with D. So a dilation of 3/2, then a reflection, and it flipped across this specific line, which is the y-axis. Okay, moving it forward. All right, so for this one, they want us to give a dilation that would map ABD, the original, onto ACE, the dilated image. Okay, so if you notice that it's only a dilation alone, okay, it's just a dilation. So it's a dilation, and then we can figure out by how much. So I'm going to use my little ruler, and I'm going to figure out by how much. So if I measure this bottom half, it's 3.5. And if I measure from here to here, well, it comes out close enough to be 5. So I'm going to call this 5 centimeters. So I'm going to figure out the scaling factor. Remember, ABD is the little one, AC is the big one, this is the pre, this is the next one. Okay, so 3.5 times something should give me 5. So all I do from here is divide. Divide by 3.5. Divide by 3.5. And I get a really funny number. So I'm going to see if I can't convert that to a fraction. And I can. It's going to leave it as 10 over 7. So that's what I'll leave it as at. K equals 10 over 7 would be the actual scale factor. Usually they're not like that. Usually they're nice numbers. Okay. So it would be a dilation of 10 over 7 with A as the center. How do I know that again? A didn't move. B dropped to C and D dropped to E. Okay. So in part B, we want to circle the proportion that is incorrect. Right? So we do know that angle A is going to be part of both the little triangle and the big triangle. So we want to start matching these as far as the corresponding side. So if I do this as 1, 2, 3, 1, 2, 3. Okay, AC you can see as your big. Okay, A to C is the 1 and then the 2. A to B is the small. That's also 1 over 2. Okay, so we got big over small. And let's check here. C to E, yep, that's the big. And C to E is 2, 3. This is 2, 3. And this is the big. And then we have BD, yep, that's the small. And B to D, yep, that's 2, 3. So we had big over small equals big over small, and they are the corresponding sides. measure of angle A is both the big and the small. So that one's kind of tricky. Okay, we'll just match the bottom ones. ABD here. Okay, ABD was 1, 2, 3. And so was ACE. ACE was 1, 2, 3, according to up here. So we know that ACE is the corresponding angle. It does match it, and A is the same. So this one's good. This one's good. Let's check this one. A to D is the small, and AD is 1, 3. Okay, AE, yep, that's the big. And AE is 1, 3, yep, that matches. Okay. AC, ooh, uh-oh. AC's the big 1, 2. And AB is the small 1, 2. Well, we can't do small over big equals big over small. So this is the incorrect one. All right, so for the bottom, we've gone over these. The 3 primary properties of dilation is, remember, multiplying by the original by the scale factor to get your primes, where K is the scale factor. That your original shape to your new shape should be parallel, and that the angles are preserved. All right, if you have any questions, please see me in class.